Hey guys, in this video, I'm going to teach you how to analyze the graph of a polar equation and determine which parts of the domain of the function will produce each of these three petals on what looks like a three-leaved rose. All right, let's get started. So first what I did was I just created a table that goes by 30-degree increments from 0 to 180. And the reason I chose 30 is that I want to be able to focus on these simple quadrantal angles. And I know that 30 times 3 will give 90. So that's why I chose to go by 30s. All right, so let's plug in each of these values into the equation, figure out what R value we get, and then connect it to this graph. Let's get started. When theta is 0, you get 3 times 0, 0. And the cosine of 0 is just 1. Times 4, we get 4. So when theta is 0, R is equal to 4. And that just corresponds to this point right here. At 0 degrees, we're at 4. So theta equals 0 corresponds to that point right there. All right, let's keep going. When theta is 30, we do 3 times 30 is 90. So now we're here, and the cosine of 90, of course, is 0 times 4 is 0. Our R value is 0. That means we're 0 units away from the pole. We are at the pole. So that point right there corresponds to when theta is equal to 30 degrees. All right, now let's do 60. When theta is 60, 3 times 60 is 180. The cosine of 180 is -1. Times 4, you get -4. All right, so remember, if theta is 60 degrees, that's pointing in this direction. But we want to go the opposite direction by 4 units. So 1, 2, 3, 4. This point corresponds to when theta is 60. All right, let's do one more value. So when theta is 90, we do 3 times 90, 270. So the cosine of 270 is 0. Times 4, we get 0. So the R value is 0. Again, that means we're 0 units from the pole. We are at the pole. And so this part of the loop, this part of the curve, corresponds to where theta is equal to 90 degrees. All right, so if you wanted to, for example, figure out what theta values you would need to use to get this petal in our rose, you basically start at 30 degrees at the origin, and you let theta increase all the way to 90 degrees. So when theta is in between 30 and 90, you get this petal of the rose. All right, and you could keep doing the same thing, going by 30-degree increments, filling out your table, and you could figure out what theta values will produce this petal and what theta values will get you all the way back to where you started. Let's go ahead now and make a connection and just sort of check our work. So we think it's between 30 and 90 to get this petal. Let's see if that's confirmed by using our GeoGebra app. So here again is the equation, 4 cosine 3 theta. And we saw when theta was 0, there it was at the start. And let me just slow this down a little bit here. So I'll stop it at 30. When theta is 30, it's supposed to be at the origin, and it was, just like we figured out in our chart. When theta was 60, we thought it was supposed to be all the way the furthest possible distance from the pole, and it was. And when theta comes back to 90 degrees, boom, we're back at the pole. So yes, we were correct. 30 to 90 generates this petal. I'll let it keep going just so you see the full graph. Between 90 and 150 gives you that other petal. And between 180 and 360, it's actually going to trace the graph completely a second time. Cool stuff. All right, I'm going to show you one more item really just as a bonus, which is, where does this curve even come from to begin with? Well, if you have one circle rolling around inside another circle, let me show you what I mean by that. I'm just going to let it roll around. And if you've got a point outside it like that, if you watch and see the locations where that point can go, I think you're going to recognize the curve that it traces